All right, everyone, we're back. Your host remote here. I'm happy to be here. Day two of the PX4 Developer Summit. Next up, we have an interesting session. We have is it a drone? Is it a plane? No, it's Jetman by Julian Lecourt. He's calling in from Lausanne, Switzerland. He holds a doctorate in robotics from EPFL and currently working as an R&D engineer at Flybotics. He's the science and engineering consultant for Jetman Yves Rossy, helped the Jetman develop a hover flight stabilization system for jet-powered wing and intuitive pilot wing interfaces on body movements. In this session, he will show how the PX4 ecosystem enabled the world's first VTOL flight with wearable wing capable of a maximum speed of 350 kilometers per hour and a maximum altitude of 5,000 meters. The presentation will focus on both technical and safety aspects of the project and will contain the behind-the-scenes images from test flights. I'm really excited. Please welcome Dr. Julian. Julian, this.
Oh yeah, hello.
You're live.
Hello, everybody. I'm live. Okay. Hello, everybody.
Welcome. Thank you. Go ahead.
That's great pleasure to be here today to present you this project. It was an amazing project. So let me share my screen. All right. So is it a drone? Is it a plane? No, it's Jetman. So this is a project where we have achieved the world first vertical takeoff and landing with a manned aircraft, jet-powered, that is capable of flying almost 400 kilometers an hour and 5,000 meters high. Of course, working on the manned aircraft was very intense, but that was, I think, the best project I've had the opportunity to work on. And on the top of that, Yves Rossy, who has developed the wing, is a wonderful person, and I'm very glad that I've met him. So if you don't know him, here is a short video that describes what he has achieved with his wing.
This next story you have to see to believe. The latest chapter in the amazing adventures of Jetman. This time he's really outdone himself, soaring to new heights even Superman might be envious of. Jetman will soar across Wisconsin later today.
Rossy invited us to come along as he flew beside the C-17 vintage bomber. This is the kind of formation flying you don't usually see.
It looks like Stabilization starting to make his climb. He's out over the channel. There is no turning back now. He is over the English Channel and underway, ladies and gentlemen. Yves Rossy has landed in England.
Yves Rossy.
And why jets? Why not propeller-driven aircraft? Because I don't want to become a salami.
So if you look up in the sky around the U.S. and think it's a bird, it's a plane, no, it's Jetman, everybody.
All right, so pretty impressive, right? When you've done all this, what do you want to do next? I mean, flying, formation flight with aircraft, going in the Grand Canyon, crossing the English Channel. Well, Yves Rossy has been dedicated on a journey to feel the flight like a bird would do. Well, we're talking about very specific kind of birds that have jet engines, but yeah, that's the idea. And one missing part is VTOL, vertical takeoff and landing. Right now, a flight looks like this. You go up using a helicopter, and then once you reach a safe altitude, around 1,000 meters above the ground, then the pilot jumps out of the helicopter, then gains speed, and then it can fly and do loops, whatever it wants. At the end of the flight, it has to open a parachute to go down safely. What would be awesome would be to remove the helicopter from the equation. That would reduce the cost tremendously and also make it way cooler. And even better would be to also remove the parachute. So you don't need anymore to be an experienced paraglider to operate the wing. But that's pretty challenging. So what do we do? How do we get there? First thing we need is safety. So you'll see throughout this presentation, safety was always first, and it should be. And up until before this project, Yves Rossy was always flying at high altitude because that's where you have the safety of the parachute. If you are higher than 800 meters above the ground, you have the time to open a parachute in case something goes wrong. You even have the time to eject the wing, which will then land with its own parachute and open a second safety parachute. When you go down close to the ground, that's where it's getting really dangerous. So I will say it once, maybe repeat it during the presentation. Do not try this at home unless you really do what you're doing. It's very dangerous to fly close to the ground. And you will see that we have taken all the measures we could to ensure the safety. And PX4 was never the last remaining safety measure. We always had a backup. Right. Second thing we need is power. Obviously, if we want to take off vertically, you need to sustain your weight and even more. For this, we are covered because the wing is now equipped with 4 JetCat engines that each deliver 55 newtons of 55 kilos of thrust. Considering that the weight of the wing plus the pilot plus the fuel is 180 kilos, that means that you have a thrust to weight ratio larger than 1. You can go up vertically at 180 kilometers an hour, which is the speed that you fall down when you do free fall. All right, and last thing you need is control. Here, I'll take a step back and mention something that I haven't yet. There are no flaps on the wing. Yves Rossy wants to feel the flight like a bird, and he uses body movement to control the flight. There are no joysticks, no flaps on the wing. In order to roll, he twists the shoulders to go left or right. If he moves the torso forward, it will pitch down, torso back, pitch up, and move the head to do a bit of yaw. And that's it. And actually, there were tests done in the wind tunnel that showed that the wing design should not be stable. However, this particular design was used to cross the English Channel. So that's to tell that having a human on board actually controlling the platform is really something different from what we are used to do with drones that are entirely rigid and robotic platforms. So knowing that, the first trial was made without any stabilization system. And here you can see, all right, now that you've heard the noise, I will mute all the videos. What you can see on this video is that the thrust is controllable manually. There is only a potentiometer in the hand that controls the thrust. And that's enough to control the altitude. However, all of the other axes are not stable enough. On a roll and pitch, it drifts very quickly. And on yaw, you have no control at all. So the solution to that is, the solution to that is to use a thrust vector system. So thrust vectoring nozzles here in red on the drawing were added in order to deviate the airflow left and right and front and back on 2 of the engines in order to make the flight controllable. Then, as I said before, the idea with this wing is to be as intuitive as possible, to let you control the flight as if you were flying. You should not feel the wing behind your back. And the way we achieved this during hoverflight is the following. The wing here, pictured with an airfoil, is stabilized in order to stay level, like it is on this picture. And then when the pilot will move its torso forward, it will offset the center of mass forward, which will be considered as a disturbance from the point of view of the controller. Wind gust, body movements are all considered disturbances for the controller. Then, as a reaction, the controller will align the thrust vector with the center of mass so that the platform does not tilt and the wing remains level. But now we have a new stable equilibrium point where we have a forward component of thrust, which means the platform is moving forward. So that makes it very intuitive to fly. You move forward, the platform moves forward. You move backward, the same thing happens. The tilt vector will move and it will move backward. Right, so let's put that in practice. We need a test pilot, and I'll introduce you Chuck. Chuck was the brave first test pilot of the platform. And although he's made of plastic, he is nonetheless a very proud and talented pilot. The test with Chuck allowed to tune roughly a PID controller that was then used on real flight with Yves Rossy on board. So here you can notice a safety harness that limits the movements of the pilot so that it can never touch the walls, both on the top and on the bottom. So we have taken measures so that nothing wrong can happen. Here you can see the wing flying with the stock PID of PX4. No big change in the code, just some tuning. So one might say that the tuning is not correct. And here I will pause. Whoa, yeah. Just a reminder that things can go wrong very quickly. So it was very important to take the safety measures for that. Yeah. So that's the closest we've been to an incident. It was nothing bad, but we are happy that we have taken safety measures precisely for that type of event. Well, I was saying that some might say that the tuning was not great on this flight, and they're probably right. But the thing is, you have to consider that each flight is only a few minutes, and we can do only 2, 3, or sometimes 4 flights per day because it takes some time to prepare. And it requires up to 5 people to operate, like to have all the safety measures we wanted. So it was very time consuming to tune the controller. So instead, the approach that I've taken was to do some system identification. Here, we are looking at roll and pitch jerk. that were measured from the flight I just showed. So in blue, you have the measured jerk. And in orange, you have the predicted jerk predicted from the actuator movements. You can see that we can have pretty good modeling of the platform. And this was used in model-based control that replaced the PID controller existing in PX4. And here I wanted to show this short video because this was the first test of this new controller. And it was a very nice moment because you can see in his eyes that, well, that's the moment we both knew it would be working, right? He's testing the strength of the controller, and then here, yeah, he knows that it's really strong and that it will work. So that was very exciting. Okay, now that we have something that is able to stabilize the flight, we need to prepare for outdoor flight. So a bit of architecture. In the wing, we have a PXOC that has a few custom applications running. The first one is called a JetGuy command. It's basically an application that replaces the commander. We wanted to have as much control as possible on the behavior of the system. And we could not afford the system to switch mode, I don't know, like go to land or disarm without us knowing. So what JetGuy command does is when all the safety checks are passed and the button is pressed, it then forces the system to off-board mode. So it's an off-board mode that is triggered by onboard applications. It's a bit backwards, but it's the best way we found to have a good control on the behavior of the system and be sure that it follows our state machine. So speaking about that, I'm very excited about the ongoing work on state machines because it will make PX4 much easier to comprehend and easier to assess what the behavior of the system is. Right now, that was the best solution for us. There is also a JetGuy control, which implements the controller and button that handles the button state. On the left, we can see that we have added a second PXOC in the helmet. And this PXOC also runs custom apps. One use is to provide information to the pilot through an LED about the state of the system. And the second use is to give commands to the controller, yaw commands and a bit of trimming on the roll and pitch. And on the right side, we have non-critical parts of the system, which is a Raspberry Pi running a web server, exposing the state of the system, and then a smartphone on the ground that is very useful when we set up the system to know that everything is fine, all the estimators are healthy, and all the batteries are charged. Okay, and with all this, here is an example of the kind of flights that we achieved. This was, I think, about a year ago today. So let me fast forward a bit where it takes off. Oh, if I can. No, I can't apparently. No. Well, the point is, it's very, very stable. And according to the pilot, it's very easy to fly. You don't have to do a lot of crazy motion to stabilize the system. You just lean backward and it moves backward. Then you turn the head and it just follows. Move forward and it moves forward. That's apparently very, very easy to fly. All right. Then we prepared for the outdoor experiment. Removing the safety barriers one by one, always being precautious. So the first test was going outdoor with a light breeze and with the upward anchor removed and but the downward wire was kept for safety. Then we did first hops on the boat. So thanks to Sagra for lending us the boat. It was very great. It was a short flight, but it was the first that was completely unfettered. It was very, very exciting. And the whole team was super happy after that. And finally, here is the flight that we've done on the shore, the first vertical takeoff, completely autonomous, no remote, no joystick, only body motion to drive the flight. Okay, great. So what next? At the beginning of the presentation, I promised you that we could remove the helicopter from the equation, take off from the ground, have fun in the air, and then land. We are not quite there. Actually, here I highlight all the zones where we have flown. So very low on the ground, less than 2 meters above the ground. We have flown a bit higher above water, because in case of failure, that's a safe splashdown. We have flown higher than 800 meters, because that's where you have the safety of the parachute. And there we tried forward flight, vertical flight, transitions, both ways. All works great. Yves has also developed a ballistic parachute that allows to open a parachute down to 200 meters altitude. But there, the vertical flight was not tested yet. And what's missing is the blank area you can see between 10 meters and 200 meters. There, we don't have a system to ensure safety yet. And that's somewhere we will not go until we have the safety measures to go there. So if you are a manufacturer of a system that provides safety down to 10 meters, then please contact us. Otherwise, we will not do that for now. And if you see anyone doing it or claiming that it's okay, it's, according to me and to Yves, it's just irresponsible. It's just taking too much risks. Right. To finish the presentation, I would like to show you this short video because I find it wonderful. It was after trials of transition at high altitude. Yves spotted a nice cloud and decided that the test session was over, and he started to climb 4,000 meters altitude and started to play into the clouds, which is very wonderful. Yeah, on that video, I will look at your, I'm sure, many questions, and I thank you for your attention.
Hi, Julien. Can you hear me?
Yeah, I can.
Thank you. Awesome. That was awesome. Let me share some questions from the community with you real quick. Can you do me a favor? Can you unshare your screen for now?
Yeah, I can.
Yeah.
Yeah.
While we wait for those questions, community, please go to the PX4 Slack channel for the PX4 Dev Summit. I want to invite Julien here in live on stream. He's on the hook now, so Julien, can you go to the Slack channel and share some of those videos with the community? That would be really cool.
Yeah, I'll do.
Awesome.
I'll do. Yeah.
All right, so questions. Thrusters, are they electronic, fuel-based? If so, which fuels?
So the thrusters are fuel-based. These are gas turbines that run on jet fuel. So if the question was about the environmental aspects, yes, it pollutes a lot. It consumes 30 liters in 8-minute flight. So it is gas-based, but the power to weight ratio of these gas turbines is just unbeatable. You have a gas turbine of 5 kilos that produces 55 kilograms of thrust, and it's all contained in a small package. You cannot afford to have large propellers on this platform. So for now, that's the only solution.
Great, thank you. Another question is, what is the reason behind the decision to not have control surfaces?
So that's by design. The goal, according to Yves, was to get out of the cockpit. When you are in a cockpit, you are driven by the aircraft. You move the joystick, and then some mechanics happen. The aircraft moves, and then you follow the aircraft. On this wing, that's the opposite. You are moving, and then the wing follows you. So it's completely different feeling, and that's the goal of the project.
Great, thank you. Okay, so I'm going to leave some of those questions for you to answer on Slack. There's a lot of good, interesting questions, but I think they're better answered by you on Slack asynchronously. Thank you again for being here today.
All right, thank you
for your presentation.
And I look forward for the following presentations. Thank you.
Awesome.
Bye-bye.
Thank you. All right. Hi, your host here, Ramon speaking. Please join me in thanking Julian Decour. I'm concerned by Chuck's safety now. We gotta check on that safety pilot. And just a quick note before we continue, please, like Julian said, don't try this at home. This is done by professionals. Don't try this at home. That's not why PX4 exists. There's a reason, there's safety embedded into the application. Please be safe at all times.